Welcome to the 12th lecture of combinatorics. So, we were discussing this problem in the last class. Determine all integer solutions to the equation x1 plus x2 plus up to x4 equal to 7, and the xi's are all greater than equal to 0, that is non-negative integers. And now, how many possible ways we can get solutions to this, or how many solutions are there for this thing, right? So, now I am claiming that this is the same as the problems we were discussing in the last class. What was the problem? The first problem was, right, there are n objects, we call them the n type of objects sometimes, or maybe sometimes we say that n type of objects, and each object has lots of them, right? You can take any number of them from that type, or we just say that n objects, we can take the same object several times. Repetition number of each object is infinite, you can take any number of times if you want. And we want to make a selection of r things. R things have to be selected using this from these n things only, just that some of the things can repeat, and this right, the things are allowed to repeat, that is what. Now, this number was the possible number of ways to make selections of r is r into n minus 1 choose r, right. Then the second way, which is essentially the same problem, was as a balls and boxes problem, balls and bins, balls and containers problem. We have r identical balls here, identical balls in the sense that we cannot distinguish one from another, identical balls, right. And we have n distinct boxes, n labeled or distinct boxes. You can differentiate one box from another. Now, how many ways you can place these r things into these n boxes, right? Some boxes can be empty here. We saw that the number is r plus n minus 1 choose r, the same as above. Here you remember this r, the number of identical balls corresponds to the size of the selection we are making in the earlier problem. The n label boxes correspond to the types or the objects the type of objects we can take, right. So, the repetition is captured that in the many balls can go into the same box, and then we considered a variation of the problem. For instance, like when all the boxes have to be non-empty, then it is r minus 1 choose n minus 1. This just by a simple application of the earlier result, right. First give each box one object, and then apply the same formula, and we got it, right. This one r minus 1 choose n minus 1. Now, we are saying this third problem, namely this problem of finding integer solutions x1 plus x2 plus c xn equal to r. Is the same here, which each xi has to be greater than equal to 0. So, to illustrate the problem, we just took a special case, namely x1 plus x2 plus x3 plus x4 equal to 7. See, because what to illustrate here, it is just that we want to show the nature of the things. For instance, 0 plus 1 plus 2 plus 4 equal to 7. So, that here x1 equal to 0, x2 equal to 1, x3 equal to 2, x4 equal to 4. This is one solution. But note that, for instance, if I had taken 1 plus 0 plus 2 plus 4, this is a different solution, because this x2, x3, x4 and x3 are getting the same values. x2 is getting different value now, because earlier it was 1, now it is 0, x1 is getting 0, so x1 is getting 1 here, right. So, the order in which we write this is important. We are allowing zeros, and we need 4 terms including zeros, okay, of case, but the order in which we write it is important, because the ith one, ith number we write here will go to xi, right, xi is assigned to that. Just that we are using the same numbers is not enough, right. That is a different problem. How many, for instance, if we do not give importance to the order, we are only interested in which numbers we are using to form 7, and that is a different problem. It is a partition problem, right, that we will discuss much later in the course, but as of now we should understand that this is different. For instance, if you want to write down all these things, of course we can try to do that, but rather than trying to do such an enumeration and waste time, we would try to establish the correspondence between this problem and the earlier problems, so earlier 2 problems, right. So here you can see that x1 plus x2 plus x3 plus x4 equal to 7 is the equations. Now let us have 4 boxes. This box is labeled x1, this box is labeled x2, this box is labeled x3, and this box is labeled x4. Now we have 7. These 7 things, that means it is like in some problems we considered 10 rupees is being given to people, right. Sometimes we considered 7 bananas are being distributed. So here there are just 7, that this number 7 is essentially 7 units, 7 ones, right, 1 plus 1 plus 1 plus 1, 7. So we can think that those ones are given to each of these things. So this we can, or in other words we can think that there are 7 identical balls here to get a correspondence between the earlier problem. Now the question is, the 7 identical balls, some of them should go to this box, some of them should go to this box, and it should distribute that 7 identical box. The number of boxes which went into this box will become the value of x1. The number of balls which went into this box will become the value of x2. The number of balls which went into this box will become the value of x3, and the number of balls which went into this box will become the value of x4, right. So therefore this is the formulation, right. This is same as the earlier problem then, right. So the how many ways we can distribute the 7 identical balls into this distinct 4 boxes, right. You can also put 0 into some of them, that means there is no ball going into this, right. So you can see that is exactly the same problem. So for instance, if you want to, therefore the answer will be the answer to the earlier problem, namely 7 will be equal to r, and then this n will be equal to this will be r plus n minus 1, choose r, right. That means 7 plus 4 minus 1, choose 7, that is 10, choose 7, right. This will be the number. General answer will be this. Now okay, if you want to see the correspondence between the other problem, selection problem, so the x1 plus x2 plus x3 plus x4 equal to 7. We are in the selection problem, we just say that we want to select 7 things, right, and this is one type, this is one type 1, right. This is another type 2, this corresponds to another type, this corresponds to another type 3, right, and this corresponds to another type, or maybe another object, you can say like that. This is the first object, second object, third object, fourth object. We are taking several times the same object, or we are taking so many things of the same type, right. The question is, we want to take 7 things of this type, this type, this type, or this type, right, and then how many we take of this type will become the value of x1, how many we take of this type will become the value of x2, how many of this type we take will become the value of this one, and how many of this type we take will become the value of this one, this x3, right. So x4, therefore, and similarly the backwards, suppose if we get a solution for this thing, it is as good as saying that we have, for instance, say x1 equal to some k1, x2 equal to k2, x3 equal to k3, and x4 equal to k4. That means we will be equivalently saying that we have selected K1 things of type 1, K2 things of type 2, K3 things of type 3 and K4 things of type 4, and of course this will add up to 7. That means we have selected 7 things of these types. That is what we mean. K1 plus K2 plus K3 plus K4 equal to 7. So, we see the correspondence. So, the answer to the general problem x1 plus xn equal to r, where each xi has to be a non-negative integer. The number of such solutions is equal to r plus n minus 1 choose r. This is the total number of possibilities. This is the post problem, and we just remember that thing, namely these 3 problems are equivalent. We were discussing these 3 problems all the time, the last class, and this class also we are continuing with it. The number of integer solutions of the equation, non-negative integer solutions, we mean x1 plus x2 plus x3 plus xn equal to r, where xi is greater than or equal to 0 for each I, and the number of selections with repetition of size r from a collection of size n, and then the number of ways of r identical objects, ways in which r identical objects can be distributed among n distinct containers. These are all the same things. Next problem we consider is okay, this is some problem where we can use the earlier one. How many non-negative integer solutions are there to the inequality x1 plus x2 plus x6 is less than 10. So, of course the obvious answer when you say x1 plus x2 plus x6 is less than 10 is what is rolled here. Now, that means there some can only go up to 9, and each xi here has to be greater than or equal to 0 as usual. Non-negative integer solutions is what we want to. Now, the one way of looking at this, so we can enumerate all possibilities. For instance, one a solution may be like x1 to up to x2 may sum up to 0, right? It may sum up to 0. So, here we know how to find out the solutions, because everything has to be 0 here, right. So, right, because there is only one solution. So, we will, our formula will also give that, because r equal to 0 here, r equal to 0 here, n equal to 6 here. So, 6 minus 1 choose 0, that is 1, right, because 5 choose 0 is equal to 1. So, the other thing is you can have x1 plus x6 is equal to 1. Here how many solutions we can get? So, instead of 6 we will put 1 here. So, instead of, because r instead of 0 we will put 1 here. So, this will give us how much? This will give us 1 plus. So, initially we got 0 plus 6 minus 1 choose 0, that means 5 choose 0. Now, we are getting 1 plus 6 minus 1, right, choose 0 is equal to sorry, 1 plus r is equal to 1 here. The type of things is again 6 minus 1, and we have 1 here, right, that is 6 choose 1, right, and then we have next one, when the next thing will be x1 plus x2 plus say up to x6, they have to add up to 2, that is one possibility, right. So, r equal to 2 plus, so 6 minus 1 choose 2, that is 6 choose 2, and then x1 plus x6 is equal to 3. So, this will become 3 here, right. So, now instead of this 6, sorry, here it was 7 choose, right. 7 choose, this was 7 earlier. So, now it will become again 8 and so on. So, we can add up all these things together and get the answer. But of course, this has a drawback. Say up to where we should do it all the way to 9, right, x1 plus x6 is equal to 9, because we know that this sum has to be strictly less than 10 integers. So, it is 9, the sum is either 9 or 8 or 7 or 6 or 5 or 4 or like that till 0. But then suppose n was this instead of 10 we had a very large number, we cannot do this thing, because this is we will have to consider too many cases. So, therefore, that is not a good idea. We would rather try to get a more general solution. So, what we will do, x1 plus x2 plus x6 is less than 10 is what we told. Now, what about introducing a new variable here, say plus x7, and then make instead of this let us put a equality. We add this one x7 and then make it equal to 10, means whatever wherever we reach here and then plus x7 is equal to 10. That has to be the value of x7, because x7 is automatically determined by what the sum takes, right. So, of course, one condition we have, x7 has to be always greater than or equal to 1. Why? Because if we allow x7 is equal to 0, then what happens is this entire sum will have to take a value of 10, which is not allowed, right. It can only take up to 9. If it is only taking up to 9, this last value has to take at least 1, right. So, therefore, x7 has to be greater than or equal to 1 is the only condition. You can see that a solution for this new this thing x1 plus x2 plus x6 plus x7 equal to 10 this time. Any solution to this thing will correspondingly give a solution to this one, because you look at this thing and take the solution to that, and now you look at the value of x7, it is at least 1, you remove it from that. Now, if you sum these things together, you will get something less than 10, right. So, that will be a solution for this thing also, this earlier equation, right. On the other hand, any solution to the earlier equation will give a corresponding solution to this, because if you have this thing less than 10, you can always find a value for x and whatever is left to reach 10, right. That will be at least 1. So, that will be a solution for this new system of equations we have written, new equation we have written, right. So, therefore, the solution to, there is a bijection between the solutions of this equation and the solutions of this inequality. So, therefore, we just have to solve this new problem instead of this problem, right. So, therefore, we concentrate on this new problem. This is a nice trick, we converted it to an equality. So, namely x1 plus x2 plus x6 plus x7 is equal to 10 now. The conditions are xi is greater than or equal to 0 for 1 less than or equal to I less than or equal to 6, and x7 has to be at least 1. Okay, x7 has to be at least 1. x11 has to be at least 1. This is the point. Now, we know how to solve it, because this corresponds to this. We cannot directly apply the previous solution, because the condition is not all xi's are greater than or equal to 0. Here x7 is at least greater than 1 more. So, we will again convert the problem to such that it comes to the form we are more used to. So, this condition we want to get rid of. So, what we do is we write a new system of equations like this: x1 plus x2 plus x6 plus x7 is equal to 10 as our system. We will write for x1 we will write y1 is equal only. So, this is y2, right. I am just converting it to another one, y6 plus, instead of here we will say that y7, but y7 is x7 minus 1, but we know this is equal to 10, right. Therefore, this has to be 9. right. We will define y7 to be x7 minus 1. See, again the point is that if you have a solution for this thing, you also get a solution to this one, because whatever value we have for y7, we can add one more to it and then make x7. So, here in this equation we just say yi is greater than or equal to 0 for all I 1 to 7, right. Here even if it was 0 initially, it will become 1 by adding 1, right. Similarly, if you have a solution for this one, we will get a solution for this, because this will copy for all of these things. For the last one, we will just minus 1 and make this, and because this was at least 1, by minusing 1 it will, in the worst case it can become 0, that is all, it will not violate any condition, right. This 10 will become 9. 10 will become 9, because here we were using x7, we are just minusing 1 here, therefore, it has to minus 1. Now, we can ask for the number of solutions for this thing, that we know, because there are n variables here. So, 7 variables here, r is equal to 9, this is r, this n equal to 7. So, therefore, we can say that it is 9 plus 7 minus 1, choose 9. This will be the answer, that is 15, choose 9, this will be the answer. See, if this is this may look like this last one is a change of variable here, but you could have argued using the balls and bins in a more concrete or combinatorial way. For instance, you remember this, each of xi corresponded to a box there. So, x1 correspond to the first box, x2 correspond to the second box, x6 correspond to the sixth box, x7 correspond to the seventh box, and so on, right. And now, if this was the situation, x1, x2, x6 and x7 was corresponding to boxes, right. When we say that x7 should have value at least 1, it means it is equivalent to saying that, and this 10 identical balls here, remember, right, 10 identical balls. So, it is equivalent to saying that the 7th box should get at least 1 ball. So, you rather give 1 ball to that box, that means this identical boxes are now only 9 left, right, because 1 ball has already gone to that. And now, the condition is that 1 ball is already given to them. We can as well think that the 7 boxes have to get this 9 balls, that means we have to distribute these 9 balls in the 7 boxes, no more conditions. If you want, some boxes can be kept empty, right. So, that way also we could have got this 9 plus 7 minus 1, choose 9, this one, right. So, this is, so but that the initial trick was worth noting, because we converted first into an equality by adding a new variable to it. Now, the next question we consider is how many terms are there in the expansion of w plus x plus y plus z raised to 10? What do we mean by this? So, for instance, if you had just considered x plus y raised to 10, we have 11 terms, namely these are the terms. So, the terms, I think terms are vaguely defined, I will just I will not try to make it very formal, but from this example you should understand what we mean. So, because the expansion is 10 choose 0 into x raised to 0 y raised to 10 plus 10 choose 1 into x raised to 1 y raised to 9 and so on, 10 choose 10 and x raised to 10 into y raised to 0. So, each of these things are considered terms. This is one term, this is second term, this is another term, right. And yeah, if this is a term, this is a term, and there are so we have, because we are starting from 0 and we are reaching 10. So, there are 11 terms in that sense, right. So, the way to attack this problem, for instance, this is trivial to say that x plus y raised to n has n plus 1 terms. So, right. So, essentially we are asking how many patterns of the form x raised to I, y raised to n minus I are there, that is what we are asking, because that first coefficient is unimportant. So, this kind of patterns, how many patterns are there, right? Clearly we know the condition is that I, this I and n minus I, they are adding up to n. That is the way we are splitting this exponents, right. So, the x raised to a into y raised to b is a pattern if and only if a plus b equal to n. That is what we are saying. This is a pattern which will appear in the expansion of x plus y raised to n. Now, this is a question of, this is the same question which we are considering, x1 plus x2 is equal to n, and each xi has to be at least 0, and then how many ways you can do this thing is what, how many solutions are there for this thing is what we are asking. And we know that because there are two terms and here n equal to r. Okay. So, r plus, sorry, the number of types is 2, 2 minus 1. So, we can write, sorry, this r is n, see this is becoming this, right, and then choose n, right. This is how much, n plus 1 choose n, that is n plus choose n plus 1 choose n is n plus 1 choose 1 is equal to n plus 1, that is what. So, very trivial enough, but we see the question, we understand the question what we are asking, and we see that how we can map it to the previous problem from this thing. So, when we come back to this x plus y plus, sorry, w plus x plus y plus z raised to n, and then we are asking for the pattern of x raised to n1 plus y raised to, so something y raised to n2 z raised to, sorry, w raised to n1 x raised to n2 y raised to n2, this kind of patterns will come, right, z raised to n4. The only condition is that, so for this to be a pattern in the expansion of this thing is that n1 plus n2 plus up to n4, okay, n3 plus n4 has to be equal to n, right, because they should add up to the total exponent. So, why is it so? Because we are writing, you remember the way we manipulated, we worked with the multinomial, we proved the multinomial theorem. We had written this as n products, this one once and again once like that, n times we wrote, and then each variable is taken. So, each term here is contributing one variable and it is forming a finally it is forming a term, right, and then we are collecting terms of similar type. So, it is like an x may be contributed first, next the second term may contribute a y, and the third term may contribute another y, and fourth term may contribute a z, and finally we will see how many x's are there, there x power that into y power that into z power that, and so on, right. This is what a pattern of this kind of a pattern will arise out of that, and you can see that because the total the number of things which is contributed, the total number is the number of terms, right, because each term is contributing 1 to a final product term, right. So, therefore, this n1 plus n2 plus n3 plus n4 has to be equal to n, that is the one, and of course, each ni has to be greater than or equal to 0, because you cannot put negative things, because there is nothing like negative thing. 0 thing is okay, because some x may not be contributed by any term to a product term like this, right. Everything, every time you may get y, that is why y into y into y into, that means y raised to n will come. That means it is w raised to 0 into x raised to 0 into y raised to 0 in y raised to n into z raised to 0, right, or it is possible that there is 2 y's and n minus 2 z's, all w and x's are zeros. This kind of things are possible, but it is not possible to have negative things. So, it is all non-negative integers. So, the exponents of x, y, z and w, right. So, they should add up to n, that is the only thing we should understand. So, now how many ways we can get these things is what, how many solutions are there for this equation for n1. Now, instead of x1 x2 I should have written x1 x2 x3, but we already use x here, therefore, we just use n1 n2 n3 n4 for the variables. So, that now number of solutions is clearly there are 4 of them here. So, the r is equal to n here, right. So, r plus 4 minus 1 choose r will be the answer, but r is n here, of course r is n here. So, in this case we used n for that r, right. So, n plus 3 choose n will come, right. So, in general what is happening is, for instance, you may be talking about something like x1 plus x2 plus xr, sorry, xk raised to n, right. In this thing, how many terms are there, how many patterns will be available. So, we are asking how many things of this sort, right, x2 xk, and then this is n1 n2 nk. The condition is n1 plus n2 plus nk has to be equal to n, and also each ni has to be greater than or equal to 0. This is the condition. How many solutions are there? Solutions are definitely here, instead of r we will use n, because there are n, this is the n equal to r here. Usually we write r here, and the number of terms is k. So, n plus k minus 1, choose n. This will be the answer, right. So, yeah, so this is what you should understand. Different ways in which a positive integer can be written as a sum of positive integers, where the order of the summand is considered relevant. These representations are called compositions. So, what I will again come back to this. So, what we want to do is, suppose some positive integer is given, we want to represent it as a sum of positive integers itself. For instance, 1 can be written as, say, just 1, right, 1 equal to 1, that nothing can be done about it, because if you take 2, you have to use a negative number 2, that is not allowed, right. So, 1 is only we can write 1 in only one way. Now, 2 can be written as, say, positive integers. You are not allowed to take 0. So, you should start with 1. 1 plus 1 is equal to 2. Yeah, that is the only way you can do it. Now, what about 3? So, this is the only way you can do it. What about 3? 3 you can start 1 plus, sorry, you have one more way. This you can also write 2 equal to 2, right. Here there are two ways to do this thing, right. And for 3 we can start with one single term compositions, that means 3 equal to 3 kind of things, and here we can also write 1 plus 2 equal to 3, and then we can also write 2 plus 1 equal to 3, right. This is also, the order is relevant here, order is relevant, 2 plus 1. Now, we can't do anything for, but then there are three length splits, 1 plus 1 plus 1 is a 3. Then we have 1 plus, because 2 should be split, right, 1 plus 2, sorry, 1 plus 1 plus 1 plus 1. So, now once you start with 1, then you have only this one, right. So, there are only four ways to do this thing, right, there is no more things. So, you can see a pattern here. This, when I used 1, this is 2 to the power 0 ways to do this thing. Here 2 to the power 1 ways. This one happens to be 2 minus 1, 2 minus 1. Okay. So, that 2 raised to 1, that is 2 to the power 2 minus 1. So, this is 2 raised to 0 is 2 raised to 1 minus 1, and here it is 2 to the power 2 ways, that is 2 to the power 3 minus 1. This 3 correspond to this 3, and this 1 here corresponds to this one here, this 2 here corresponds to this 2. It looks like that is the pattern. So, we can try with 4 equal to 4. So, what we expect is, we want to get the number 2 to the power 4 minus 1 equal to 2 to the power 3 equal to 8. This is what we want, 4 equal to 4. Now, see, with 2 splits, with 1 plus 3 equal to 4, that is why you can also write 3 plus 1 equal to 4, that is fine. 3 splits, 1 plus 3 should be split, right. So, 1 plus 2 is equal to 4, or you can write 1 plus 2 plus 1 is equal to 4, that is all there. And then 4 splits, you could write 1 plus, yeah, here there are more, in fact 2 splits. Yeah, you can also write 2 plus 2 equal to 4, this is fine. 2 plus 2 is 4, and we have 1, 2, 3, 4, 5, 6. So we have 1 plus 1 plus 1 plus 1 equal to 4. Still only 7. There should be one more. Where is the one more? Yeah, here we could also rearrange this. So here 1 plus 1 plus 2, we can also write it as 2 plus 1 plus 1, right? This is different. This is a different order, right? The same numbers, but the order is different. 2 plus 1 plus 1, so this is 4. We got 1, 2, 3, 4, 5, 6, 7, 8. 8 ways of doing it. Now we can't do anything, because here we have considered all possibilities here. We have considered all possibilities here, because we started with 1, now we are starting with 2 here, and there is only one way of doing it here, and here this is only one way. So we have exhausted. So it is true that 8 ways of 8 compositions are there for here. You remember the definition of the composition. I have elaborately done a few examples, so you should be knowing what it is now. So it's just that your a positive composition of a positive integer n is something like n1 plus n2 plus nk equal to n. We do not mind how many things are there here, but each ni here has to be at least 1. All are positive integers. Now the order is important, in the sense that same numbers we could have this you put here n2 plus n1 and then keep all the things together, still it should be counted separately. So how many possible compositions are there? This is what we are asking. So definitely then one way we see, we want to use the earlier whatever we have done before to solve this thing. So for instance, we know that when we write x1 plus x2 plus xk is equal to n, then the number of ways to do this thing is n plus k minus 1 choose n, right? But there are some differences. Here we assumed each xi is greater than or equal to 0. There we are not allowing zeros. So is it possible that I because see, if 0 was allowed, then we could have so but then we still have a trouble. How many things should be there? How many k should be there? That also we have to figure out, right? So therefore we cannot directly apply the previous thing. So what we will do is, okay, we will see all possible k's. See, for instance, k can be equal to 1, k can be equal to 2, k can be equal to n. These are the total number of possibilities. Now, so when we say k equal to 1 case, then it will be like an equation x1 equal to n, right? Here you know that there is only one possibility to this, x1 has to be n. We can say what. So for k equal to 2 case, it will be something like x1 plus x2 equal to n. The only thing is we cannot put x1 or x2 0. So each of them has to get at least 1, right? So see, what will happen is 1 is anyway given to x1. So we can, or in other words, our technique was to convert x1 into a variable y1 and x2 into a variable y2, where y1 is defined as x1 minus 1, and then y2 will be defined as x2 minus 1. That means we are allowing y1 and y2 to take zeros, but here you have to make it n minus 2, right? Because what we do is we get a solution for this, we will get a solution for this also by minusing whatever value we have assigned for x1, we will minus 1 from that, we will minus 1 from this, and we will assign for this thing. That will satisfy this equation, and then anything which satisfy this equation will satisfy this equation also, right, because we are adding 1 to it, right. This is what it is. Okay. So, therefore, so now with this n minus 2 we know how to solve it, or how much is this, because here it is like the solution of this equation here, that it is summing up to n minus 2. The answer is n minus 2 plus the number of types 1 2, right, x1 x2. So, that is 2 minus 1, choose n minus 2, right. This will be n minus 1, choose n minus 2. This is what we will get. So, we can probably write it as n minus 1, choose 1, and here this is only 1, we can write it as n minus 1, choose 0 if you want. See, you can this is just 1, we can write it as n choose 0 or n minus 1 choose 0 or whatever. In the end we will see the pattern, we can decide, right. This is n minus 1 choose n minus 2. By symmetry identity, it is n minus 1 choose 1 also, right. Now, let us see what is happening with the three terms, that is more of x1 x2 plus x3 is equal to n is what we want, but each of these xi's here has to be greater than or equal to 1. Therefore, we convert, because to use our previous theorem, we will convert it to y1 plus y2 plus y3 equal to n minus 3. Why? Because now we are allowing yi's to be greater than or equal to 0. Now, any solution of this thing will give a solution for this thing, because to each yi we can add 1 and get the corresponding value of x1. So, that will, because this is at least 0, this will be at least 1, and reverse also. If I get a solution for this thing, I can minus 1 from each of them, I can get the value for 1, just that they add up to n minus 3 now, that is it, that is what we want. So, the solution for this correspond to solution for this, and solution for this correspond to solution for this, that there is an equivalence between the solution set of this and solutions. So, there is a bijection between the solution set of this and solution set of this. So, therefore, we can see how many solutions are there for the second one, and this we know, because this r is equal to n minus 3 here. So, n minus 3 plus number of variables 1 2 3, that is 3 minus 1, choose n minus 3, which is, we can write it as, say here, n minus 1, again this is getting cancelled, right, n minus 1 choose n minus 3, which is n minus 1 choose 2. Earlier it was n minus 1 choose 1. We initially started with n minus 1 0, n minus 1 choose 0, next we got n minus 1 choose 2. Now, the next one you can see, for instance, in the kth arbitrary k term thing. So, this xk has to be equal to n, right. Now, this is, again I will do the same trick, y1 plus yk I will convert, this is equal to n minus k, and of course, each yi has to be greater than or equal to 0. Here it was xi has to be greater than or equal to 1, right. So, now as we argued earlier, we can say that there is a bijection between the solution set of this equation and the solution set of this equation. So, we just have to count the number of solutions of this, and this is, as we mentioned, this is n minus k for r plus k minus 1 choose n minus k, right, cancel k, n minus 1 choose n minus k, that will be n choose k plus 1, right, okay, k plus 1 or k minus 1. So, it will be n choose n minus 1 minus n minus k, right. Yeah, that is n choose n choose k minus 1. So, this is what it. So, for k terms you get n choose, sorry, this is not n, it is n minus 1, sorry, this was n minus 1, n minus 1 choose n minus k. So, this is n minus 1 choose k and k minus 1. So, when there was 0 term we could get n minus 1 choose yeah, n minus 1 choose. So for kth term what should we get? So 1 minute, are we getting the pattern correctly? So we are getting for 0 term n minus 1 choose 0, sorry 1 term, then there is only 1 term we are getting n minus 1 choose 1. When there are 2 terms we are getting n minus 1 choose 2. When there are 3 terms, yeah 3 terms we are getting n minus 1 choose 2. So for when there are k terms, we are getting n minus 1 choose k minus 1, right. So finally we can go up to how many terms? This will be n minus 1. So 1 term n minus 1 choose 0, 2 term n minus 1 choose 1, and finally k term n minus 1 choose k minus 1. When we have all n terms, it will be n minus 1 choose n minus 1, right. That is okay, because as you see, when there we have an equation like this, x1 plus x2 plus xn equal to n, right. The only solution is 1 1 1 1 for all of them, they add up to 1, right. There is only one solution, that is what n minus 1 chosen. And we know what this is, we have already summed up this kind of identities in the earlier classes. This is 2 to the power n minus 1, this is exactly we want to get, right. This is a general formula, right. So whatever pattern we observed was valid, so it is correct, right. Now so this was, we just used our theorem. So of course this can be solved in much easier ways also, but you should try to solve it in different ways, but we just use this to illustrate our the formula we have got earlier. So this is the number of representations here, and now we can, some slight variant of this problem. The number of compositions of 2n where each summand is even. So that means okay, maybe we can take some examples, like suppose say 10, let us say. Now we are not allowing 1 plus 9 equal to 10 kind of things, because here we have 1 and 9, it's odd. We are not even allowing 2 plus 4 plus 1 plus 1 equal to 10, because these numbers are odd numbers. These are odd numbers, we are not allowing. We want all of the summands to be even, right. So that means 2 plus 2 plus 2 plus 2 plus 2 is equal to 10, right. 6 plus 4 equal to 10, 10 plus 10 equal to 10, that is okay, right. Of course you can see that we can only talk about even numbers now. So we are taking compositions of even numbers, because if you are summing up all even numbers, we will only get even numbers. There is no point asking for even compositions of 7, because how much ever even number you add, see without adding one odd number at least we cannot get an odd number, right. So therefore we are talking about compositions of even numbers, namely 2n's, right. So for in the case of 10 is equal to 2 into 5. Now how will you solve this thing? So it is easy, just that you can see that because it's an even number. In the case of 10, let us say 10, we can say 1 is 10 equal to 10. This we can write as 2 into 5 equal to 10, right. Similarly in the for instance, when we write 4 plus 6 equal to 10, we could have equivalently written as 2 into 2 plus 3 equal to 10, right. So 2 into 2 4, 2 into 3 6, or when we write 4 plus 2 equal to 10, we could have written 2 into 2 plus 1 equal to 10. So you see, every time when you remove this 2, the remaining thing will add up to 5 only, right. 2 into 5 is equal to 10, that is the way. So actually we are, once you discard these 2's, we are looking for compositions of 5 without any conditions, because here we have the condition that all summands have to be even. Now here we have just the condition that the summands have to be non-negative. So sorry, summands have to be positive. When we are not allowing 0, of course. So and then how many ways we can do? That's we are asking. That's what we are asking, right? So, the answer will correspond to the number of compositions of 5, which is actually 2 to the power 4, as we have seen, 16. So, in general, when we are talking about 2n, we will be considering the number of compositions of n, where there is no restriction. Here there was a restriction that every sum n has to be even. So, we as we are always doing, we can set a bijection between the compositions of 2n, where each sum n has to be even compositions, we can say to the compositions, normal compositions of n, right. There is a 1-to-1 correspondence, there is a bijection between them. So, it is enough to count this is 2 to the power n minus 1, as we have done, right. So, that is some nice question we wanted to discuss. Yeah, here is an interesting question. For j equal to 1 to 20, so this is a program segment, j equal to 1 to 20 do, for j equal to 1 to I do, for j equal to 1 to j do. So, there is a loop inside a loop in the sense that it is a nested loops, 3 of them nested. So, first outermost variable is I, so then next comes j and next comes a. J goes from 1 to I only, whichever was the value of I at that time, k goes from only 1 to j. So, the question is how many times will the statement gets executed, right. So, yeah. So, see, for instance, if it was a simpler question, I equal to 1 to n. So, okay, I put 20 here, but okay, you can also say n. J equal to 1 to I. How, and then print something, say print something. How many times the print statement will be executed? This is a usual question which comes in exams and all. So, what is that? Because first time when I is equal to 1, j will range from 1 to 1, that means j will take 1 value. So, when I equal to 2, j will range from 1 to 2, that means 2 times this print statement will get executed. So, then I equal to 3, this j will go from 1 to 3 and then print will be done 3 times, and then like that up to n, and we have to sum this up. This will be n into n plus 1 by 2, right. So, but now what will you do? Suppose this I equal to 1 to n, and now j equal to 1 to I, and then k equal to 1 to j. So, we will say that this we have to sum I equal to 1 to n, then j equal to 1 to I, and then k equal to 1 to j, and this 1 is to be summed every time. So, this is only 1, we have to sum. How much is this? This is what we are asking. We are printing it once for each of these things, but what is it counting? So, okay, this can happen. See, now somehow with a lot of effort you may do it, but the issue is that you may have several such summations, not just 3. You can have 3, 4, 5, 6 or summations for that matter. How will you do? The point here is that whenever your print statement is executed, there is a value of I, right, there is a value of j, there is a value of k. Say value of I is equal to a, value of j is equal to b, there is a value of k equal to c, right. You know that a has to be greater than or equal to b, because j is going only up to I, right. So, the value j takes will be always less than equal to the value taken by I, and similarly the value that k takes will be at most the value that j takes. This will be true, right. Suppose, and how many, so the question is how many such ABCs are possible, right. For instance, if say I is going from 1 to n, the only possible values are up from 1 to n only. So, from 1 to n, how many such ABCs can be created such that A is greater than equal to B is greater than equal to C? You can see that the solution is will give you the answer, the number of this thing will give you the number of times the print statement is executed, because every time your print statement is executed, you have a value of I, value of j, value of b, that gives you such an ABC, that is A greater than equal to B greater. On the other hand, if you have an ABC such that A greater than equal to B greater than equal to C and all of them are coming from 1 to n, then of course for corresponding to that there is a point at which print statement I will take that value of A, j will take that value of B, and k will take that value of C, that particular value C, right. And then okay, of course this is all valid, it will when I is equal to that A and j can reach that particular value of B because B is less than or equal to A, and also k can take that particular value of C and so on, and say it's just enough to count this thing. So, we will stop here and we will continue in the next class.